Okay. Next that line reactance, positive and negative we have told for transmission line that positive and negative your sequence reactance will remain same. So, it is 100 ohm, line base voltage you have computed 123.2. So, 100 your into 50, that is MVA base will remain same throughout, right, into 50 upon 123.2 whole square, it is coming 0.33 per unit. Now, line reactance your this thing zero sequence, that was given actually 300 ohm. So, that is positive negative, that is 100, but zero sequence it is given 300. So, it is 300 into 50 upon 123.2 square, that is 0.99 per unit, right. So, reactance of motor 1 positive and negative sequence, same way that you just convert the ohmic value to its own base, motor's base, then the common base. So, it is that is called your new base rather, right. So, 0.25 into 50 upon 30 into 10 by 11 whole square, this will become 0.345 per unit. Now, zero sequence reactance of motor 1, that was given 6%, same way you may bring it to your new base. So, 0.06 into 50 upon 30, because motor rating is 30 MVA and 50 MVA is that common base, right, into 10 by 11 whole square, that will become 0.082 per unit. This is zero sequence reactance. Next is for motor 2. So, these are nothing actually, just you have to calculate this parameter correctly, right. So, reactance of motor 2, that is positive and negative sequence, that is 0.25 it is given 25% into 50 upon 15, because motor 2 rating is 15 MVA into 10 by 11 square, that is 0.69 per unit. So, zero sequence reactance of motor 2, that was 6% it was given. So, 0.06 into again 50 upon 15 into 10 by 11 square, that is actually 0.164 per unit. Now, reactance of reactors, it is given 2.5 ohm, that is 2.5 into 50 upon 11 your this thing, your it is actually not square, it is 50 upon 11 square, right, it is not, it is 50 upon 11 square. So, that is becoming actually your 1.033 per unit, but when you will take this diagram, when you will draw the zero sequence diagram, this 3 Zn will come. So, it will become multiplied by 3. So, it is 3.10, that we will see later. So, all these parameters actually are computed. So, this problem when you will read, hope it is covering your whole screen, right, just once again I am putting it, when you will pause it you can see that whole problem you can note down, right. So, this in this case your just hold on that. So, after making all these your calculations, just hold on here this point I missed it before when I was showing the diagram, actually this is marked as a G, I have marked it now G. So, this reference bus you have to take one reference bus. Now, this is your generator, all subtransient parameters are given for generators and motor, this is your generator. So, this is actually E G double dash, this is reference bus, any one thing you have to take in the reference, this is reference one, and this is plus minus, and this is J 0.20 for the generator. Now, this one for this transformer positive sequence one, this impedance for transformer. So, J 0.0805 remain same for negative also, when you see that. Then this J 0.33, that your that one is coming for your transmission line, this is for transmission line, that means this is the line, next line will come transmission line. Next this is for transformer 2, then transformer T2 will come. So, this is your transformer, and everywhere I am marking D to E transformer, D to E, you will not make any mistake, then D to E transformer, then E to F the transmission line. So, this is your what you call, this is your J 0.33, then F to G, that is your F to G again transformer T2, same parameter J 0.805 per unit. Then these two motors are in parallel, because they are connected to the common bus bar. This point is P, this point is Q, that means this is point is this is from transformer F to G. So, this is your F, then your transformer, then G, F transformer, then G point is coming, and these two transformers are in parallel. So, that is why it is P, and these two are P and Q, these 2 points P and Q, this is your P and this is your Q. So, this is your P and this is your Q. So, these parameters also computed for the motor, this is J 0.345 and this is J 0.69, this is EM 1 dash and this is EM 2 sorry EM 1 double dash sub transient 1, this is EM 2 double dash, this is plus minus, this is plus minus connected to the reference. So, this is the positive sequence diagram for the your this whole circuit, this is the positive sequence diagram. Next is negative sequence. So, negative sequence there is no source, no voltage source. So, in the negative sequence diagram, if you see that this one, that is your just hold on, this is your negative sequence diagram. So, reference one, look positive sequence, this voltage sources are not there, but look all other parameters are same, because negative sequence parameters same as positive sequence parameter. So, only voltage sources are not there, here it was J 0.20, here also J 0.20, here it is J 0.0805, here also J 0.8 or 0805, here also J 0.33, here also J 0.33, here also J 0.805, here also J 0.805, here also J 0.345, here also J 0.345, here also J 0.69, here also J 0.69 connected to the reference bus. So, this is negative 6. So, no voltage source, but all parameters remain same diagram without any voltage source. And now, this is for your what you call, this is for your negative sequence. Now, you have to come to the zero sequence. This is your reference bus for zero sequence diagram, right. Now, question is come from this side to, we will move to this side. Now, star is grounded and this side is delta. Although star is grounded, delta means delta, there may be a circulating, there will be a circulating current inside delta, and star is that is generator, star is grounded means that is your what you call that zero sequence current will flow, it has to be connected to the reference bus, but question is that delta is isolated, it has no neutral, circulating current will be inside the delta, and but star is grounded, that means this is reference bus, this is connected, your what you call this is your this 3.10, actually that is 3 Zn, I calculated somewhere no here, that is your 3 Zn, Zn that is reactance of reactor, that is basically it is Zn. So, this is 1.033 multiplied by 3, so it is 3.10. So, that is why this is 3.10 and zero sequence your reactance for the generator, it is J 0.06, it is given, but as it is grounded, so it is connected to the reference bus, but this side is isolated because delta, it is your circulating current cannot leave the terminal. So, it has to be isolated, that is isolated, no connection, right. Hope you have understood this. Next is line side will come, this is grounded, this is grounded, both are grounded. So, there is a path for your zero sequence current to flow, that is why this is connected to reference, this is connected to the reference, this is also connected to the reference, because both are grounded, that then in between what is happening, this transformer thing is coming J 0.0805, then your zero sequence reactance of the line is it is actually J 0.99 we have computed, and this is J 0.805, and the second transformer this one, and this is closed because this is grounded, this is grounded. So, there is a zero sequence current will flow through the line, right. So, this is your this thing and the transformer. Next is the motor. Motor is one is ungrounded, that means this will not be connected to the reference bus. So, this is motor 1, its zero sequence is given that J 0.082 we have computed, but it will not connect to the reference bus because it is ungrounded, and this motor is grounded, that means it will be connected to the reference bus. So, it is connected to the reference bus with 3 Zn, J 3.10 and J that motor your what you call zero sequence reactor, everything is given, it is J 0.164, this is there. So, this point is P and Q, this point is P and Q, this is F to G, F, then it will remain isolated, here also it will remain isolated because this side is delta, circulating current will be there, your circulating zero sequence current, and this is your star grounded, right. So, it is connected to the reference by this side, but there is an isolation. So, that means no zero sequence current can flow. So, that is why there is an isolation here. So, this is like this and this is your zero sequence network. I hope you have understood this. Only zero sequence is the major issue. Positive and negative is simple, as same as before, right. I mean, positive sequence you have a voltage source, negative sequence all voltage source should not be there, but parameters of positive sequence network and secondary I mean line impedances will remain same, but negative sequence only you have to see this grounded or ungrounded star or delta, accordingly you have to make it with respect to the reference bus. So, this is zero sequence diagram, because this is important when we will take that unbalanced fault problem. Next one is this one, that you have to draw zero sequence network of the power system as shown in figure 11. So, a small circuit diagram is given. This is generator is grounded, only positive negative sequence now easy, I am not doing it. My objective is to show you the zero sequence network, right. So, this is your delta star connection this thing, and star is grounded, this is star delta, star is grounded, and this is motor, generator is supplying this thing power to motor, and this is your star but ungrounded. You have to draw the negative sequence diagram. Parameters are not given, but you have to take something and you have to make it. So, the generator is grounded, if Zn is that your grounding reactance this one, then it will be 3 Zn, it is grounded. So, it will be 3 Zn. So, that is why 3 Zn, and say zero sequence impedance of the generator is Zg0. So, I have made it Zg0, but this side just now we have seen the previous problem, but this is delta. So, there is an isolation. So, it will remain open, this is remain open, and this side is star grounded, this side also transformer star grounded. So, it will come here, come here, come here like this. So, this is ZT1 transformer zero sequence your transformer positive negative and zero sequence reactance same, right, and this is for the line zero sequence reactance ZL0, and this is ZT2, this is all point you mark D, E, F, G, the way I marked it, right, and then you connect to the reference, and this thing is this side is delta, this side is star. So, isolation is there and it is not grounded. So, it is open, it is not cannot be connected to the reference bus, and this is Zm0. So, that is transformer zero sequence reactance. So, this is the zero sequence diagram for this power system network. Hope you have this zero sequence only you try to understand, positive negative simple. Next is this one, you have to draw the zero sequence network of the system shown in figure 13. So, this is generator is grounded, this is delta star, star delta, and this is star your grounded. There is no difference except one thing, that here previous problem it was ungrounded. Now, here we have made this is grounded, nothing else. So, here Zg0 I have made it because your this thing you are assuming that there is no ground impedance here. So, 3 Zn I have not make it, assuming that there is no Zn is 0. So, in this case it is Zg0 and this is star grounded, but delta isolation will be there. So, this is actually open, then this side star grounded, this side also star grounded. So, it is reference bus, connect this is your P, this is your R, this point is R, right, this your what you call. So, this one you can take this is your this point actually should not be R, this is your QR line. So, this is before transformer, this point should have been R, and this point this is actually Q, it cannot be Q, this point actually Q, this is Q, this is R, Q or R transmission line, by mistake I have written here. So, this is actually transformer ZT1, this is ZT1, then point Q will come, then transmission line ZL0, then your this is your then after this point R, that is your ZT2, and star is grounded. So, connect it, and here star is grounded connected, but this is delta, this is star, isolation is there. So, it cannot be connected. So, this is the zero sequence network for this kind of for this network. Next one is that figure 15 actually is a double circuit line. Look, if so far we have taken single circuit problem. Now, if it is a parallel circuit, double circuit line. So, figure 15, this is your figure 15, it shows a sample power system network. You have to draw 0 sequence network, data are given below. Actually, G1 generator 1, this is generator 1, right, 100 MVA 11 kV, XG10 is given 0.05. Now, G2 actually given 100 MVA 11 kV, XG20 is equal to 0.05, and T1 transformer 1, that means this one is 100 MVA 11 by 220 kV, and given XT1 is given 0.06 per unit, and T2 100 MVA, again this is a step down 220 by 11 kV, XT2 is 0.07 per unit. Line 1 XL10 is 0.3 few, this is the line 1, right, double circuit, and your this is line 2 XL2 is 0.30 per unit, and this is the diagram. You have to draw the your 0 sequence network. So, this generator is grounded, again delta star we have taken here, right, and this is double circuit line, parallel line, and this is star star, both are grounded, and this is also generator star or grounded. Here this Zn is given, actually J 0.02. So, this one is given. So, this we have to multiply by 3, because it will become 3 Zn. So, it will become J 0.06, and here also J 0.02 is given. We will draw the your 0 sequence diagram, it has to be multiplied by 3, it will be then 0.06. Now, question is that I mean you mark all the point, like there is a P before transformer, after this Q, this is E, this is F, this way first you mark and then move step by step, then you will find things are very easy. So, 0 sequence diagram, how things will be then, that first thing is that this is you draw the reference line, and this is star grounded, but this is delta. So, there will be an isolation, and before showing this diagram I will give an exercise to you. Instead of delta star, you take star star transformer, but star grounded, both this side primary side you take star and star grounded, and please draw the 0 sequence network of your own. But for this problem, and these are all star star grounded, these are all star grounded, this is also star grounded. So, there is absolutely there is no problem for this drawing this 0 sequence network. So, what we will do, this is your reference bus, this is your reference bus. So, generator actually this is J 0.02, so 3 Zn, that means J 0.06, and isolation is there because star grounded, but this is delta. So, connectivity will be there, and this is given J 0.05 is given, and this is 3 Zn, that is 0.02 is given, multiply by 3, but there is an isolation, but as star is grounded for the generator, so you have to connect it to the reference bus. Now, next is that transformer, that P point, right, this is P is open, after that the transformer, this side you have to consider. So, delta star, so T1 XT1 is given, so this is J 0.06, that is given for transformer 1 0.06, it is given, but as is both are your grounded, both are grounded. So, 0 sequence current will flow. So, that is why it is connected here. Now, after this double circuit line is there. So, two parallel circuit you draw. So, line 1, it is Q, this is Q and E. So, in between this thing two parallel line. So, this is J 0.03, J 0.03, both are equal, both that is also given, this is 0.3, both the lines it is given. Next is that your transformer T2, this is star star this thing. So, it is your J 0.07, and as this side is star, generator 2 also this side is star grounded, this is also star grounded, that means that this is 3 Zn. So, J 0.06. So, this has to be connected to the reference bus, and this one your this transformer this generator 2, it is given Xg20 is 0.05, that 0 sequence reactance is given. So, that is why after that it is J 0.05, and this point will be F, and this is star grounded, this is also star. So, 0 sequence current will flow. So, connectivity will be there, star grounded, here also star connectivity will be there. So, then you connect this transformer J 0.07, this is the second transformer J 0.07. So, J 0.07 and connect it to the line, just connected it to the line. So, this is the 0 sequence diagram for the your what you call for this kind of problem. So, positive negative I am not drawing because it is easy, but zero sequence one is important. So, I hope you have understood this this kind of problem. Right. So, so this is this. So, another example of this kind of thing. So, you draw zero sequence network of the sample power system shown in figure 17. I will show you. Data are given below. Xg0 is given, your motor also is there, Xm0 is given, transformer T1 also given, X22 is given, line 1 that is equal to both two lines are line 1. Actually, it is not line 1 is equal to actually it is line 1, line 2 is there, both are there actually. So, line 1 is equal to this one. So, I can say line 1 is XL10, that is XL20, two lines are there, both are actually equal your what you call equal reactance. So, this is all parameters are given, you have to draw the zero sequence diagram. In this case same thing, but no delta or star delta transformer. So, it is star grounded, all star grounded, but this is ungrounded, that motor. So, reference bus you will take. So, generator star is grounded. So, it is actually for the generator no Zn is given. So, you just J 0.05, here it is data are given. So, J 0.05, right, and your transformer that just let me see whether this Zn is given or not. No, it is not given, and for transformer 1 it is 0.12 per unit. So, that is why 0.12 per unit, and it is all this diagram that all are star star connection, right, all are star 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 grounded except this motor. So, start from the reference bus, this is transformer T1, it is given, then this double circuit line both are given, J 0.70, J 0.70 given, then your this is also star star, right. So, that is also given for this transformer, it is 0.10 given star star. So, this is the point this is the point A, after that this is ungrounded. So, there this is motor is J 0.03, this is ungrounded. So, there should not be any connection, there will be an isolation. So, but do not make the mistake, suppose you will come up to this, after that you will make connection like this, and this is ungrounded, you will make isolation, it is not like that. This side is star star, so you make it, this is grounded, but this is ungrounded. So, take J 0.03, then you make this portion is open, because this is ungrounded. So, this is your what you call the zero sequence diagram. So, all the versions, right, I have shown you, and this is the last one, looks like this is the last one, another version, that you draw that zero sequence network of the sample power system and shown in figure 19. This is your figure 19. So, you have a generator star grounded, you have a point mark here P, A, L, M, N, E, Q, G, A, F, U, all I have marked, you mark of your own. This is delta star transformer, star is grounded, this is star delta, it is ungrounded, delta star transformer, star is grounded, but this here star is grounded, delta transformer, but here star is not grounded, and here it is star. So, in this case you have to draw the zero sequence network. Look. So, what you will do, you take this reference bus, I have taken here at the bottom now, so that it will be easier for me to draw. This is the bottom now, then it is Zg, suppose it is given. So, it will be 3 Zg for the generator, and generator 1 Xg10 will be there. So, it will because it is grounded. So, it has to be connected to the reference bus. Then your this side is delta, for line 1 it is delta, and for line 2 also it is delta, delta star both are grounded, but as it is delta. So, there will be isolation. So, make this one, and then your LM I have showed as if it is not, it is isolation, there is no connection here. Then this star here grounded, star here grounded. So, consider line 1, star 1 grounded. So, it is connected here to the reference one, right. Then x t 1 you take, consider this x t 1, then consider line 1 x L 1 0, then transformer x 2 you take, x t 2 you take, x t 2 you take, but here star is not grounded, star is not grounded, that means it is isolation, there will be, it is open, because it is star is not grounded, it will open. And if you come to this side, this generator, that this generator, this generator, this star connected ungrounded. So, it should not be connected to the reference bus, it is x g 20, right, and this is your E and F point, E and F point, but this is delta also, complete isolation. So, that is why this is totally open, this is totally open, and because delta I told you that even if circulating, I mean even if circulating current will be there, but that cannot leave the your what you call that delta terminal. So, it will be isolation, and for the line 2 when will come, this is also grounded line 2, this is also line 2 x 2 3, then this line is actually x L 20, right, and this transformer is x t 4 the transformer 4, but this is actually grounded, star is grounded. So, it is grounded. So, this way this is that your what you call the 0 sequence network of this your this example. So, this way you should little bit practice, then things will be easier for you. So, with this we have completed that your symmetrical components. So, one symmetrical component is and all sort of positive sequence and negative sequence and 0 sequence, all sort of things I have showed you, but positive sequence when you are drawing the positive sequence, same as the way you draw the circuit diagram with voltage sources. So, that is very simple, and for negative sequence actually almost say it is same, all the positive negative sequence impedances for all the components more or less say it is same. So, only voltage sources should not be there. So, two very easy, positive and negative, and 0 sequence component that you have to consider, but because 0 sequence actually you have to draw it correctly, and if when you will see the fault studies, then you and when you will try to solve it using positive, negative and 0 sequence components, at that time we will see its your what we call usefulness. So, symmetrical component is more or less completed, and another thing I told you regarding that your A matrix inverse. So, very easy to remember that A inverse is equal to 1/3 A conjugate transpose. So, you know A matrix. So, you can easily make it A inverse. So, next we will begin that your unbalanced or unsymmetrical faults. So, unbalanced or unsymmetrical fault actually occur in a power system. Actually, these are the faults very common, because in the previous we have seen 3-phase fault, that probability of occurrence of that fault is very rare, but this kind of fault is very common. So, one thing is that Sun type fault, another is series type of faults, but Sun type of faults actually single line to ground fault, that is one thing, it is very common, but another thing is that line to line fault, that is also common, sometimes double line to ground fault. So, these 3 faults are very common, and as you know that that generally that for 3-phase short circuit or 3-phase fault, the fault current is very high, but sometimes that single line to ground fault also, that current is as severe as your 3-phase fault for a particular thing, that if the fault occurs near the generator terminal. If the single line to ground fault if happens near the generator terminal, then that severity will be almost like your 3-phase fault current, right. So, but simultaneous occurrence of 2 faults, for example, say phase A to ground fault and phase C to ground fault, this probability of simultaneous occurrence of such fault is very rare, or line to ground fault 1, another phase, suppose phase A line to ground fault and phase B and C line to line fault, these occurrences are very rare. So, we will not study those things. So, that probability is almost negligible. So, anyway, so Sun faults basically single line to ground fault we will study, line to line fault we will study, and double line to ground fault. An example of series type of fault is open conductor fault. Suppose suddenly conductor has opened, right. So, this is very rare, but one conductor open or two conductor open fault we will see, and we will try to analyze it using symmetrical component. So, unbalanced fault analysis actually is very important. This is more this because the occurrence of this fault are very very often. So, in that case, that unbalanced fault analysis is actually basically important for relay setting, single phase switching and system stability studies. So, we have because these are the faults very common. So, next we will see single line to ground fault. Thank you, I will come again.